Hey everyone, thank you for joining. I'm just going to give people a couple more minutes to roll in and then we'll get started. Hi everyone, thank you so much for joining. I think I'm going to just take one more minute and then we'll get started. First of all, I just want to thank everyone for taking the time to take some time out of your day to learn more about the Rockfall monitoring system. It's a product that we at LB Foster were pretty passionate about, and I really can't wait to tell you all more about this solution. It's pretty exciting. It's an innovative solution that is solving a problem that I don't think anyone else is really doing, especially in the way that we're doing it. Um, so just a little bit about myself. My name's Will Becker. I'll be your presenter today on this informational webinar. I have a background in the Class 1 rail space. I used to work for Norfolk Southern. I was with them for about 5 years and then went over to LB Foster. And during my time at LB Foster, I've been the technology sales engineer and kind of leading some of our effort when it comes to the adoption and implementation of Rockfall monitoring at Class 1 railroads and at shortline railroads as well around the United States and Canada. And so it's a product that we're pretty excited about. Um, I think, first of all, I just really want to uh, paint a picture of why this is so important to us. So I have a visual for everyone from a train last year. This is a train that was coming around the tracks at speed around a curve, and this is what they see. And this is some news footage that I saw from the track view, and this is exactly what we're trying to avoid. So that rocks on the tracks, they're coming around a curve at night. It's not possible to stop. And one thing that I did want to note with this incident is that this was in a location that had no form of rockfall protection whatsoever. And so this issue of rockfall monitoring and the need to monitor our tracks at risk, it's a hazard that seems to be increasing and it's happening in places where it didn't happen in the past. And so looking into that, what we see is that this hazard is getting worse. A global study was done on rockfall and rockfall events throughout the world. This includes landslides over the past 100 years. And what you can see is that there's a pretty clear and steep increase in rockfall events in the late 90s going into the early 2000s and onward. And part of the reason for that is, as global temperatures rise, we're seeing that soil loosen up and these rockfall events become more common. Additionally, around the world, and many of the people who are on here operate in territories where there are these issues, we're seeing more fires and more frequent heavy rainfall events. Both of those conditions do lead to a higher frequency of debris flow, rockfall, these conditions that we're trying to avoid. So when you think back to the picture that I had shown you, this was in a location where there was no form of protection and it hadn't been a rockfall area for the railroad for some time. Now, when I say protection, I'm generally talking about one type of technology, and that technology is the rock slide fence. So this technology, it's been around for a very long time. The the way that it works is it's a series of wires that is strung up along the tracks. And then when those wires are broken, it can indicate there was a potential of a rock that has broken through those wires and fallen onto the tracks. As I mentioned, this is the industry standard. It's what you see at most railways. And it's an old technology, been around for 140 years. First was deployed in Scotland, came over to the US, and it is what you'd expect to see when we're talking about rockfall protection. Uh, as far as the monitoring side, there are some solutions as far as mitigation, but when it comes to monitoring, this is your bread and butter. And so, I think a question that a lot of people might ask is why have we seen so little innovation in this space where the technology is 140 years old? It must work really well, right? And so we had a really unique opportunity about a year ago to take a look at a slide fence network at a major class one and their entire network over the course of the year, understand every single activation that they saw. They tabulated exactly what caused their fence to activate, along with some other key metrics. And so, what you can see on the graph here is that most of these slide fence events were caused by benign incidents. So, when I'm saying benign, I'm talking about things like a tree branch. You can actually see in my picture on the left hand side or on the right hand side that there is a tree branch that's, you know, in those wires. Something like that can cause it to break. Lots of the time, these fences break and it's really not known what causes the activation. Plenty of small rocks. If it just hits a wire just wrong, it's going to cause an activation. Things for like wildlife. But the true reason that these are used is that there were 10 large rocks that fell on the tracks and it caught these 10 large rocks. And that's been why this technology has been used. Now, that being said, I said 10 true events here, but there actually were also two missed detections in this period. Luckily, these two missed detections did not result in derailments, but they are rocks of a size that could have caused a derailment that were found on the tracks and trains stopped short of them. Um, you know, these are incidents that are absolutely critical to be stopped. And the problem with slide fences is that so much of their efficiency is down to their design. So are they tall enough? Is the wire spacing correct? Do they have the right canopy? Can a rock bounce over a fence and land onto the track? So when you think of a slide fence, I think one thing to think is they alarm a lot. They do a pretty good job at catching the true events, but every once in a while one will slip through if that design isn't perfectly right. Now, I said that this railroad, they gave us a lot of different metrics, and some of them were related to their operational efficiency. And so what we saw was hours of network delay. On this railroad, they had trains that were lined up in a way that in their crucial corridors, you could be seeing as many as 9 to 10 hours of network delay for a slide fence event, particularly certain fences that were more remote. It could take hours and hours, potentially even days, for those fences to be repaired. And sometimes in the winter months, when there was ice buildup on the wires, those fences were just down for weeks at a time. Each time one of these fences activated, a lot of the time this is call out labor, overtime work, not expected or planned. And every single one of those activations on average resulted in about $2,500 of labor costs. And so when you have a network of slide fences and you're experiencing hundreds of thousands of false activations in a year, this cost can really add up really quickly. And so this was kind of the, I guess, driving factor. Once we have did all this research into, what the status quo was and where the industry is when it comes to rockfall prevention, this is what drove us to look into new solutions to not only uh, bring down costs from these delays, but also increase safety from those missed detections and in increasing areas where you see these rockfall events. And so, what we brought to the market is a pretty cool technology. and it's what we're calling our LB Foster rockfall monitoring system. So what you can see in this picture here is that there are a series of our LiDAR units placed strategically along the tracks to scan the entire track. And the basis of the system is what we call our Insight LiDAR. When we look at our Insight LiDAR, the way that it works is that we're sending out beams of light, and we're doing that in 100 feet in every direction. So in the graphic below, you can see it sweep through the scan, and each one of those beams represents 100 feet. It is scaled down just to fit on this slide. We're doing that 20 times per second, or 20 hertz. So we're really getting, almost instant pictures of what's going on the track. Now, we selected a specific LiDAR that has 120 or 190 degrees of scan. So what this allows us to do is put it pretty close to the track. And if you have some curvature that curves in towards the LiDAR, we can actually see a little bit behind ourselves. So it allows us to be more flexible with our LiDAR placement. And then finally, what you're seeing on the screen here is a 5-degree separation between the beams just for visualization, but our actual spacing is 0.25 degrees. So you'd see 20 times as many beams on one of our scanners. And so really, we get a really dense coverage of the entire scan area. Now, translating this to what it looks like when we put this on a railroad track, what you see is that we cover the entire railroad track. The length that would be shown here is around 170 feet of track, since we are cropped at the ends. And then noticeably, if you look towards the top of the picture, a lot of the beams are going out. Some of them are even going so far out, and they're striking, in this example that I chose here, an embankment. Potentially, this is the embankment that they're looking at monitoring. And what you might notice is that there's a pretty large shoulder at the top of the screen, and potentially rocks could come down this slope, land in this embankment. They would pose no hazard to rail operations, but they are getting picked up in our scan field. So it's something that we identified that we want to limit our scan zone to only focus on the portion of the track that we want to make sure are clear of rocks for safe trade travel. And so that's what we call our detection zone. And what we do is we shrink down the zone. The beams are still traveling that full distance, but what we do in our software is we define the zone and we call it our detection zone. And only obstacles that land in this zone will generate an alarm. Now, we want to be really safe about anything that lands in the detection zone and be sure that we're picking it up. And so we went with a safety critical design using safety critical components. And part of that inherent design is using redundancy. And so what we'll do is we will add a LiDAR on either side of the main LiDAR to have redundant and overlapping scan field coverage. What that looks like in practice is like this. And once again, I do want to call out the fact that we have 20 times more beams than what's shown in this example. So you can imagine that coverage of scan beams, and the scan field is a very, very tight mesh. And any obstacle that enters that scan zone, we're seeing from multiple angles, multiple beams, and really able to determine the precise object size and position in the detection zone. So generally, that's how the system works. When it comes to the rockfall monitoring layout, what you can see here, and I'll start in the bottom left for clarity, is that inside of a signal house or a bungalow, we're going to have our control rack. In that control rack, you're going to have local control of all of your LiDAR. That's where your maintainer is going to interact with the system, and a VLC that will give out an indication of a clear or obstructed track. Leaving the bungalow, you're going to have two main cables. The first one will be a 24-volt DC power cable. That 24-volt DC power cable is running your power to our trackside junction box. And then we also will have a fiber and or Ethernet cable. The reason why it's or there is sometimes these bungalows may be far away. And so if that trackside junction box is greater than 300 feet away from our signal house, we're going to run fiber. If it's closer than that, we can run fiber or Ethernet. We're given that option. From that trackside junction box, we're gonna take all of that and run everything from there through a PoE Ethernet out to each LiDAR unit. So this makes the wiring to each LiDAR independent and also adds simplicity to the wiring. What you can see is that optionally, and we would recommend it, on the trackside junction box or nearby, we're going to be placing a PTZ camera. And what's pretty cool about that is that any alarm that's triggered in the detection zone, that PTZ camera, because we have a precise size and position of that obstacle, it's going to automatically pan over to that obstacle, take a picture, and send it to whoever needs to know. That way they immediately can see that this is the object and this is where it is and this is what I need to respond to. So there are a lot of cool features that come with our system. I think most notably is, this system is always on. It's always scanning. As a requirement, where a rockfall could happen at any time. And so we have 24/7 monitoring. Anything that falls into our custom detection zone, we're going to alarm on. But that being said, there is a potential for certain other things to enter the detection zone that you may not want to alarm on. So, for example, if you were to have some wildlife walk through the detection zone, we do have a function in our system that can tell the difference between your moving obstacles and obstacles that come at rest. And we're only going to alarm on obstacles that are of qualifying size and come at rest in that detection zone. All in all, we're going to put that in a ruggedized protective housing. In our housing, I can tell you from experience, is ruggedized. We have taken many hits, direct hits from rock falls. It's even been hit by on-track equipment, and the LiDAR continues to operate as expected. And then finally, we have automatic alerts. So you're going to get head and shoulders more information from a rockfall monitoring system than you would from a slide fence. You're going to know exactly what caused your alarm. And when it comes to our outputs, I'd like to just go over the options that we have. So currently, there are several different methods when it comes to our outputs. The bread and butter output would be, we have a clear unobstructed relay inside of our unit that's controlled by the Vital Logic controller. That can be inputted directly into your track circuitry or your signaling system to indicate whether your track is clear or obstructed for oncoming trains to safely stop before they obstruct it. Additionally, we generally would recommend that we do have cellular or data communication to these rockfall monitoring sites. As an additional feature of the system, those pictures that I was talking about, those can be sent directly to your control center or dispatcher via email or text message. And so what we do is we would package that up into an email or text message, and then a list of people for every site. So let's say you had a site that you had a couple of maintainers plus a dispatcher that may want to be notified. You'd put them on the list through our web portal, and they would be getting those alerts. And then lastly, there is the online portal. And so every single system will come with the online portal. What you do is you log in, you are able to see all of your sites and able to see the real-time condition, get on that PTZ camera, see any active alarms, and really understand the status of a rockfall monitoring system in real time. And just because I think, it's a pretty system to look at, here's another picture of one of our rockfall monitoring installations. We have installations throughout the United States and Canada. This installation here is at a location called Devil's Throne in New Mexico. So one thing that I did want to touch on is that the rockfall monitoring system really has been tried and tested in a variety of environments, from the desert out up to the Canadian wilderness out on the Pacific Northwest. This LiDAR platform has been truly tested. Another thing that I think is good to note is that this LiDAR platform has been used in beyond rockfall monitoring. It has a pedigree that started in 2010 when we were using this at grade crossing monitoring systems. The backbone technology and backbone of the rockfall monitoring system has been tested at over 120 crossings, and that's really what brought us into this object and obstacle detection space. So the LiDAR aren't the only components that come with a rockfall monitoring system, and I did want to go through some of those. So other major components, obviously you have the LiDAR head assembly, and generally what we would include is the mounting posts and brackets, plus that trackside junction box. And that trackside junction box, one thing I should mention, it can handle up to 8 LiDAR per junction box. So you're going to get one junction box per up to 8 LiDAR. Additionally, we would generally include a camera and illuminator that's recommended with every system. And finally, we have a new and upgraded control panel. And that control panel has basically everything in it that your maintainer would need to service the system. So when they interface with the system, they're going to go into the signal house. They're going to look at that control panel. There's an integrated screen on an HMI where they can see the status of any LiDAR that are in alarm, any maintenance activities that are needed for the site, and easily diagnose and maintain the system from that control panel. So I want to take some time now to just go over the installation component. The installation of the Rockfall monitoring system comprises of several key activities. So first of all, there's the mounting of the LiDAR. So once a site has been selected, a LiDARs need to be mounted, and the first LiDAR would begin at the very beginning of where the Rockfall potential area starts, and obviously the last LiDAR would be at the end of that zone. That will give us the redundant coverage. Generally, what we space them at is around 90 feet between each LiDAR. So if you had 200 feet, you'd be looking at around 3 LiDAR to do that. So you'd be one more than the needed, so 90, 180, and then you would be adding a third LiDAR to get that 200 feet and redundant coverage. Those LiDAR, the first thing that's important is that they're all mounted at around the same height. So we're going to put each LiDAR up at the desired height. Generally, we're recommending 24 inches above the top of the tie. Once they've been mounted at that height, we want to make sure that all the LiDAR are scanning at a level plane. And so what you can see in the picture on the right is that we have what's called a laser area checker, and we would put that on the tracks at 24 inches above the top of the tie on 2 different places and make sure through our adjustment bracket that we are adjusting the roll, pitch, and yaw of the LiDAR to hit the middle of that uh, laser area checker at the 24 inches as recommended. And then finally, you would repeat that process down the entire section of track until all LiDAR are leveled and pointed over your detection zone. So the installation is fairly straightforward. Once you get into the rhythm of installing these things, that adjustment and alignment process probably takes around 20 minutes per LiDAR and go through the entire site until you're completed. Now, the biggest advantage that the Rockfall monitoring system is maintenance. This is the biggest advantage it has over a slide fence. And so the maintenance is fairly light. As needed, we recommend that you clean the lenses. So that's a visual inspection. And potentially every 6, depending on environment, up to 12 months, we recommend that you're cleaning those lenses. Along with that, on a 6-month basis, we're asking that you do a visual inspection of the entire site to check for damage, infestation, um, check the condition of all your seals, vents, and fans. And then at the 12-month inspection, do a more thorough system check. You're checking the main panel for voltage drops, checking for damage to the post, and checking for any movement of equipment. That would also include ensuring the alignment of all LiDAR at a 12-month inspection period. And that pretty much covers the rockfall monitoring maintenance as far as it's needed. Now, one thing that I also want to go back to and cover is that um, when a rock does fall on the tracks, this is where you're going to get the greatest maintenance gain. The only thing that's needed to reset the system to normal operation is removal of that rock from the detection zone. Once the rock is removed, the system will automatically assess that the zone is clear and go back from being an alarm to a clear state. And so compared to any other technology, the resetting of the system is very seamless. Now, I had I know that Meredith, who helped me organize this, said that after this process was completed, we could move on to a Q&A. Meredith, can you help me get some questions from the audience for any questions on the system?
Yeah, of course. I'll just type, there's actually a Q&A chat, so I'll just type a little message, and if anyone has any questions, they can do it in there, and then I'll help facilitate.
Okay, great. Thank you.
Okay, well, the first question, are you using a single laser profile or a multiple laser profile? If single laser, why not a unit that can give a 3D view of the track?
Oh, perfect. That's a great question, Dan. So the number one reason that we're using a single laser profiler or 2D LiDAR is that we feel that our output is most reliable when we're reducing the custom information and training that we need for each site-to-site basis. So I'm actually going to go back a little bit to just to our overview here. One of the things that we found is that this kind of layout with a detection zone and a 2D LiDAR um, is that the setup is going to work from site to site to site. We would expect that this detection zone, which we define generally to be 6 to 7 feet from track center in either direction, is going to be clear at every single site that we go to, and that if something is in that area, that we can very quickly make a determination that there's an obstacle on the track. And so really we went with the 2D LiDAR rather than the 3D LiDAR because it's just more it's more reliable at every site and requires way less custom work for each site to install and configure the system. And that leads to really high system reliability when it comes to obstacles that we see in the detection zone and feeling confident that those obstacles are something that we should be alarming on.
Okay, next question. Is this Buy America compliant for federal funding?
Yeah, great question, Chad. So this system, while a lot of the components do come from overseas, we have used Buy America um, funding for the system in the past. We did an installation that was federally funded. Um, Typically, the way that this is done is that uh, there's no equivalent U.S. technology that meets this requirement. And also, as we've been developing this technology further, most of it, when we started installing these back in 2018, was produced in the United Kingdom. And in the past few years, we've actually been bringing a lot of the technology back into the United States. And today, the system is being produced in Dublin, Ohio. So the answer, that's a long answer, but the answer would be yes, we could get Buy America funding for this technology.
He also had a second follow-up question. Is this solar an option for remote locations that don't have AC power?
Yeah, so that's a great question. Generally, the answer is no. And the reason for that is that the system is always on, as I think I had mentioned. And so, one thing to note when you're looking at a system, it's really going to depend on how long it is. The draw on the system is fairly substantial. So, we're looking at 25 watts per LiDAR sensor. Um, and then about 150 watts per processor and 20 watts for the trackside junction box. And so just given that draw, the requirement generally would be more than what you we'd recommend for a solar array. I'm not saying it is impossible, but it would need to be fairly large.
Okay, thanks, Will. Next question. How many systems or units do we already have installed? And then how do we protect the equipment against theft and vandalism, which is a risk in many countries?
Yeah, for sure. So today, when it comes to the Rockfall monitoring system, we have 3 systems installed today, and we're about to install a 4th one here in about a month or so. The way that we protect the equipment against theft and vandalism is that the LiDAR itself, that ruggedized housing, we can protect the LiDAR um, in various ways. That ruggedized housing does have a lock on it that we can put over it to make sure that the units can't be easily stolen. And then additionally, just with secure hardware, there's a couple of different types of hardware that we can use to reduce chances theft and vandalism.
Okay. Did you ever look at stereoscopic camera setups? What made you settle on LiDAR?
Yeah, a great question. So the number one thing I would say that made us settle on LiDAR is the reliability of the output, especially in adverse conditions. So I kind of want to backtrack a little bit here to our history with LiDAR. In starting in 2010, we started using a LiDAR platform, and during that time, we also looked into some camera systems for obstacle detection at grade crossings. And one of the things that we found is that the LiDAR performance in adverse conditions was just more repeatable. Um, I know that there are advances in camera technologies, especially with the stereoscopic camera technologies. But the number one thing with the LiDAR is that the amount of learning and training that goes into um, goes into setting up the detection zone and understanding what area of uh, a track is needs to be protected is much lower on a LiDAR system. So the way that I'd like to think about it is that we know this detection zone is going to look the same to our LiDAR site after site after site. And so that high degree of repeatability lends itself to being a safety critical system, whereas we feel like the camera systems potentially could do a fairly good job at detecting rocks and maybe even reliably. But when it comes to making that safety case to prove that it will always detect a rock every single time in all conditions, I think that's a really hard case to make. And as such, we pivoted towards the LiDAR because the inputs and variables are much lower. And so we can test out more of the edge cases with a LiDAR platform.
Okay, we have another LiDAR question. If the 2D LiDAR plane is set 24 inches above the top of rail, does that mean that the minimum object size detectable is about 36 inches in diameter? And how could this detectable size be reduced?
Yeah, so the 2D LiDAR plane generally is set 24 inches above the top of tie, which means that the minimum object detection size is also that 24 inches. In general, we have gone much lower than this. The one thing that I will say is as you get closer to the ground, the more potential objects that you don't care about come into play. And so I think a good example is we did an installation with a customer where we went way down low. We were just around 2 inches above the top of the rail. And one of the things that they found is that they were getting valid activations from obstacles. Specifically, there was a embankment that was kind of rising away, but in the detection zone. And so objects that were only a couple of inches tall that built up on that embankment edge would trip and trigger the alarm. And the problem is that those would be considered valid alarms. But at the end of the day, the customer didn't really care about them. And so when you start getting alarms at that size, the question is are they a hazard to the train? And in this case, the answer was no. And then the system's going to tell you any qualifying obstacle that is of that detection size. And so where we've really advised that 24 inches above the top of tie is based off of a study that was done on derailments and the minimum size of obstacles that can cause derailments. Unfortunately, I can't share too many details on that. It is under an NDA, but there was a large scale study that was done to determine the minimum size of hazardous obstacles to train derailments, and that's kind of where we set that plane height.
Okay. How many parallel tracks can this system handle?
Thanks, Dan. That's a good question. So it can handle multiple parallel tracks. The real question is spacing of LiDAR. In most of these layouts, you are seeing a scale that's much smaller than actual. And so one thing that I would like to point out is that these zones that are in here go way further out than I'm showing. And in general, as long as we're getting double coverage, we can cover as many tracks as we'd like. The one thing that where you may want to put another system on the other side of the tracks is if there's a high potential for trains to stop in between the LiDAR scanner and the further track. If we were to do that, the system would correctly uh, give an assessment that it cannot determine the other side of the track to be clear. So to err on the side of caution, it would generate a caution signal to oncoming trains until that train on the nearest track were to clear. So that would be the one caveat, but we can do double tracks. Theoretically, we could do triple tracks. The main factor is really, um, what's the likelihood of traffic getting in the way and obstructing your field of view? I hope that makes sense.
I think that's all of the questions that have been submitted so far.
Okay. Well, I think I want to leave everyone with one last thing then, if that's the last question, and feel free while I'm talking, if you have any other questions, feel free to ask them now. Um, First of all, we're very excited about this technology, and we are planning on doing a pretty good demo of this technology at the ARIMA conference in Louisville, Kentucky next month. So that's something that we're very excited to show off. If you are interested in learning more, we will have a large display there in a live demo where people can come see the technology working in real time. And then the second thing that I wanted to add is after this, I'm going to be sending an email to everyone who attended just with my contact information. And I really would like everyone to just, take the time and think, is this a technology that is worth considering? And if the answer is yes, feel free to reach out to me and I can go over how Rockfall monitoring would work in your application more specifically, go over any concerns that you might have, and really go from there. If it gets to the point where you really would like to look into this more and potentially get a survey done, that's something that LB Foster is always willing to do. And we'll go out there for free to take a look and give you guys a good assessment of what rockfall monitoring would look like and get you some budgetary numbers.
Looks like we have 2 more questions. Just came in. How long is the lifespan on these systems?
Yeah, that's a great question. So in general, the LiDAR systems, we'd expect to support these for a very long time. I know that's kind of a flimsy answer, but I would lean on some of our other technology solutions. LB Foster, we're the provider of our most, I guess, incumbent technology, or not incumbent technology, but our most legacy product, that Salient Systems, where the Rockfall monitoring system is sold out of, is our wheel impact load detector. And we've been supporting those systems for over 25 years. The LiDAR platform, we do know is reliable and operates for at least 7 to 10 years before those LiDARs are replaced. And then that LiDAR replacement process, those LiDARs are piece parts that could be replaced while the main infrastructure can stay in place. And so that's kind of how we would continue to support that as the system ages.
Okay, the next question is, does the system require recurring support costs from LB Foster for the life of the system?
Yeah, that's another good question. So that's really up to the customer at the end of the day. We do offer various levels of support packages. We offer support from the level of we go out, we do all the maintenance on the system. We give you a certificate of health every year, making sure that that system is good to go. And that does come with parts discounts and service discounts throughout the life of the product, as long as you are or as long as you're paying into that support package. Now, that is not required by any means. At the end of the day, the system is going to give you a clear or obstructed indication via relay output. And so if you would like to run the system without some of our fancier features like the web portal and the web hosting and the cameras, that you could operate the system with no recurring costs at all. That last question, Meredith?
Yes, it was.
Okay. Well, perfect. I just want to thank everyone once again for taking the time to join us today for the Rockfall Monitoring informational webinar. And as I mentioned before, if you have any questions, feel free to reach out to me. I'll be sending everyone my contact information. And feel free to visit us at the ARIMA show in September. Thank you very much, everyone.